the starting point. Example number 4. First, let's look at our question. Log. Here, look at the log. Log of n belongs to little o of n. We know the meaning of little o. Take the ratio of two functions, then calculate the limit. And when n goes to infinity. Okay, all right. Here, remember, in our typical function, n is discrete variable. Remember the last time I talked about discrete variable and continuous variable when we calculate the limit. The reason why we need to consider discrete variable and the continuous variable, because there is a big method called the L'Hopital's rule, using derivatives to do the limit calculation. But if you want to calculate the derivatives, you have to use the continuous variable. All right. So here, let me switch to, here at the beginning, I plan to apply L'Hopital's rule. L'Hopital's rule, indeterminate form. First check. The ratio must be an indeterminate form. Infinity over infinity, indeterminate form. That's correct. So we can go to the next step. Here, remember, we replace n by x. After this replacement, we know now we have a continuous function, x continuous variable, so we can consider derivatives. So that's the reason we use continuous variable. All right? Here, let me talk about some comment at this point. If you read our textbook, in this situation, the textbook does not use the rigorous math. Okay? The textbook still uses the discrete variable and taking derivative for discrete variable. That's not rigorous. Okay? So that's some problem in the textbook. Okay? We want to do the rigorous math, so we change here. We use the continuous variable here. All right. And we know when we use the log of n, the hidden base, we assume a greater than 1 hidden base. There is some constant, a greater than 1 as the hidden base. Okay? All right. So later, so you will not have question. I couldn't find the base number. That's the hidden one there. Now, L'Hopital's rule, numerator derivative, denominator derivative, denominator very easy, just 1. The numerator, you need to find the formula. Okay? 1 over that denominator, the base, natural log of that base, That's the reason we need a greater than 1. In that assumption, natural log of a is a positive number times x, the variable x. All right. After simplification, after simplification, we have this expression, 1 over constant times x. Now when x goes to infinity, it equals 0. Try to follow. If you have the background knowledge, the derivative you can find either from web or from some calculus book. Okay? So you need to find somewhere if you cannot memorize. Most of you probably cannot memorize derivative formula, but just find it. Okay? All right. After that, then by the definition of little o, limit definition of o, yeah, we have the conclusion. Yeah. So that's example number 4 for this part. Yeah. Yeah. If you have a question, just let me know. Yeah. All right.